Bristol. So Appolinaire has been working in and researching robotics for over a decade, much of it here in Bristol. And he's come to us today to give us some insight into how being a roboticist is probably a lot more about people and humans than you might think. And the line, not all doctors who help people carry a stethoscope, really applies here, I think. So thank you very much for agreeing to do this, Appolinaire. Thank you for joining us today. And I shall hand control of proceedings over to you. Thank you.
Thank you very much, Liz, and thank you for this great opportunity to speak, I guess, quite openly about my research, because I think usually most of the time researchers tend to stay in the lab, and you're giving me a great opportunity here to reach out outside of the lab and hopefully, yeah, share a bit of what I've been researching on, and hopefully inspiring some of the people in the audience. So I will, I guess, start a presentation right away, because I believe we are just about on time, aren't we? Yeah, okay. I believe you can all see my screen. Can you all see my screen? Yeah? I hope you can.
We can hear you and see you. Thank you.
Yeah, perfect, lovely. Thank you. Just double checking before I start, talking about stuff and actually you can't see anything at all. Yes, so yeah, so as Liz said, I'm a senior lecturer in mechatronics here at the University of the West of England, and I also have the great pleasure to also do my work in the UK largest facility for robotics, which comes with a lot of, I would say, a lot of expectations, but at the same time, with a great and an immense privilege to be, working with industry, working with other research laboratory, both nationally and internationally. So it's yeah, it's a great pleasure to be part of this robotics laboratory. So the actual title of my little talk here is Bioinspired Robotics and Rehabilitation. And I've got a little subtitle underneath that because I think this is probably where this whole research is actually going, towards robotic enhancement for amputees, trying to give to amputees what they thought they lost forever. So that's kind of the ultimate aim of this research. Now, I'm going to take you back a little bit back in time, where probably some of you might remember the 80s, if you all sort of were born in that sort of years, or even before, if you all enjoyed the 80s. Well, around the 80s, a little boy was being born, and that was in a town called Paris in France, where he really enjoyed chocolate. So yeah, these talks actually starting with chocolate. Yes, the reason why I'm talking about chocolate is because this is where this whole envy and this whole desire to understand how things work started. It actually started with Kinder Surprise. So I'm sure you're all familiar with Kinder Surprise. Those little eggs with chocolate, and they've got inside those little toys. Those little toys that you have, most of the time you have to make, you have to build yourself. So a little boy back in the days was enjoying much chocolate at the same time as the actual toy inside, and kept on asking the question to his father, what is that kind of work? What are the people that are actually making those things? And when they actually said engineer, these people are engineers because they design things, they make things. And this is where this whole journey started for that little boy, thinking, okay, oh, engineers, they actually make stuff, or they make things. Okay, I want to know more about engineers and what they do. So this is kind of where my actual journey started with engineering in general. Then few years later, give it a good 3 decades later, I've ended up designing bio-inspired prosthetic joints for amputees. Now, in between those years, what I've learned is that engineers are, above all things, problem solver. They solve problems. They come with solutions. And the whole point of what we do with students here at the university is all about training. We are training people to become people that can actually solve problems. One of the lines that I keep on saying to my student is, yeah, at the end of this training, you'll be all problem solvers. Your manager is going to come at the end of your studies with a lot of problems. It's going to be your job to solve them. So what we're giving you here really is the tools. We are giving you the tools to actually solve tomorrow's problems. And there are a lot of problems these days that we have to face. But I think it's a great opportunity. We are at the stage in this whole period where a lot of things can raise from what we know and from what we don't know. And I think engineers are here for that. They're here for enabling people to be empowered, to be able to see situations differently, because ultimately an engineer has to come up with a solution. Now, robotics. Let you dive a bit further now into robotics and what actually I do. So I the whole point of this research I've always been about bringing together robotics, but not only robotics, how we can make things smarter. So the initial scope of this all research that I've been doing for about now, about 9 to probably say actually 10 years now, started from I want to do more for humanoid robots, because robots are great. They are very cool. People see them as cool. They can be a bit frightening sometimes. You know, if you think about the Terminator, you may have that sort of robot in mind. Not really the best friend you want to have. Well, actually, you want to have it as a friend because it's meant to be coming and saving you. But never mind. But robots usually are usually seen as almost our counterpart, but we don't really trust them. And one of the reasons why we don't trust them is because sometimes they don't behave like us. Now, having done some my actually studies in mechanical engineering, then I decided to do my research in mechanical engineering applied to robotics. Now, between the 60s and the 80s, again back in time a little bit now, there was a large number of robots that were capable, and they were actually developed regarding developing. We were developing them to make things much easier for human beings. It was all about that. It was all about developing devices for industry so that they can manufacture better. They can also be more efficient. If you think about those assembly robots, if you think about those painting robots, as you can see in ads, in advertisements, or think about the packaging robots, all of those were all made for industry so that they can be much more efficient and efficient. However, we know for a fact that the state of the art in microtechnology, in sensor technology, in also manufacturing advances such as 3D printing, you're probably all familiar with 3D printing, smart materials, signal processing, and all the rest, they have raised a great demand for innovative solutions, targeting new areas of application. So this is the reason why researchers in the field, they've all recognized, they've all acknowledged the fact that this is becoming more and more difficult to realize a mechanical design that can keep superior energy efficiency with a high number of what we call actuators or motors. Now, it has become a lot clearer that usually, in engineering, and it's exactly the same with advances in control, they can't fully compensate for poor physical agent. So whatever you design, you're always going to end up with a system that would require the structure to be moved, or will require the physical system to be in action, to behave in a particular way. So a truly efficient smart system, such as a robot or a rehabilitation device, will require mechanical as well as artificial intelligence. So ultimately, we are going towards that. We're going towards artificial intelligence embedded in control, but also embedded into the structure itself. Now, the principal aim of this whole work is basically to do that, to provide a better understanding of the fundamental functions of what we call the biology, nature, and be in a position to extract those beneficial features from nature and then conveying them towards, well, a greater technological level. So taking inspiration from nature, understanding how nature does it, and then ultimately then developing and making the technology much more efficient. So a bit of a headlines for the talk. So what and why, some aims, how I'm doing this research, and the impact that this research actually has had over the years. Now, one thing that I want to clarify right away is I started with robotic, but then I've actually ended up working in rehabilitation. So I am a roboticist, as Lee said, yes, but most of my work now is really dedicated towards rehabilitation. What is it that we can do to develop devices that are going to be at the same time as useful, but also functional? What we develop needs to have a purpose and needs to be usable by the one who's going to be at the end of that chain. So the actual patient, the actual user. So ultimately, all my years in robotics have actually led me to work towards developing better rehabilitation devices. Now, let me take you back, obviously, into what I've done first. So, robotic. What have I done in robotic? What are those different exotic things that I've come across when it comes to robotics? Well, you're probably all aware of some of those robots. You probably have seen them on TV, or you may have come across some of them. So one of them here, I don't know if you can see my mouse, but hopefully you can see it. The one at the bottom in the middle is the snake robot arm that we've got here in Bristol in Osteo Robotics. A company who was actually working in inspection. So we use that arm basically to inspect areas where we can't or don't want to go. We have as well in robotics, the very famous Assimo Robot, from the Asimov author that actually came up with the rules when it comes to robotics, what a robots can or cannot do. So this is Assimo at the top left here that you can see, who's actually holding an actual stick here to actually is meant to be mastering an orchestra. Well, some people are confident with that, others not quite. But again, we're working towards that. And you've got the other applications where robots are actually greatly used in terms of military use and also in hospital. And that one is just a very fancy one that can actually walk and roll around. So he would actually rotate those little wheels, and all of a sudden he can actually start a sort of swimming motion around. It's a pretty cool robot, that one. Now, researchers, okay, they are actively engaged in developing what we call wearable devices. So when it comes to interacting with human beings, so either via a machine, what we call a human-robot interface or human-robot interaction, or about developing devices that patient can actually wear, they usually take into consideration the increasingly embedding control that needs to be provided with the device. So how are you going to be controlling that device that the patient is going to be wearing, or are you going to be controlling the device the patient is going to be in contact with? Now, that itself make devices very clever, very smart. Now, on the other hand, we obviously know that we are limited. Engineers are limited, we are limited. And whenever we come up as a solution, yes, let's just face it, we sometimes just don't do things correctly. And there's always a need to make things better, because let's just face it again, we're not perfect. We can't make things perfect the first time around. So there's a number of iterations that goes with engineering as well. So engineering is great. Engineering can almost, I was about to say, save the world in a way, but we need to do things in an iterative manner. Now, that limitations on space and power that we've got with all those devices mean that the artificial limb that we tend to develop around robotic structure would require, or they must be, highly optimized for mechanical performance, especially in areas that we call areas of purely mechanical, the mechanical aspect of them, which involve stiffness, strength, friction, or backlash, or even endurance. So you want to develop a system that is actually embracing or combining those different aspects of mechanical engineering, where you will have to develop a system that will have to compensate for these once exposed or once in the field. Now, that's the reason why we want to mimic biology. Mimicking biology is one thing, but going a step further, what is it that we can learn from biology in order for us to develop systems that will help people? I came across and I came up with that because one day I met someone that changed my mind of, I'm going to say, very narrow-minded researcher that actually think that he can just work in the lab and it's all about what I do in the lab that actually matters, and it's about what I'm going to be producing from that work that is the center of the world. Well, where you want to say, good, it's great what you're doing in the lab, but ultimately what you're developing, what you're designing needs to have I want to say, a greater purpose. You want to develop system for people that I believe again will benefit from it, because otherwise, well, what's the point? What is the point of doing what you're doing? And I came across, I realized that when I met someone who was on his way to the Paralympic Games. At the time, obviously, I didn't know any of that. I just happened to being a very noisy and a very, I'm going to say, for a very straightforward individual that asks a man by a swimming pool, oh, I can see you've got a device here next to you. What's that? Oh, yes. Sorry, who are you? Have you been introduced? Well, no, sorry. I'm a roboticist, and I work at the Bristol Robotics lab. And you are well. I'm training for the Paralympic game. We're going to be happening in Rio next year. Why are you so interested in this device that I'm wearing? That is actually enabling me to walk. Oh yeah, because I actually make joints for humanoid robots. I told him, and he said, oh yeah, oh, wonderful. So you work in that lab in Bristol? So yeah, the robotics lab. Oh, wonderful. Okay, so you make joints for machine? Yes, precisely. Yes, I'm trying to develop machine, and I was going all on about what I'm doing, what my research is all about. He listened to me for about 5 minutes, and he said, okay. What about us? What about amputees? What about people that actually do not have a leg, do not have a joint, do not have the ability to walk as they were before, do not have the feeling of having a device that enables them to just walk or to just jog or to even just kneel when I want to be with my kid, or to just walk the dog, or just go up and down the stairs. What about us? And I was just speechless. I didn't know what to say. He said, then he asked me a question, said, could you just explain why this joint that I have do not look like an actual knee? Can you explain why this mechanism is nowhere near what my knee is about? Because I know the knee has a specific specific aspect and specific shape. Can you explain why this joint can't just really bend, or why do I need to change joint when I'm going from cycling to running? Why can't I just have one joint for doing everything? Yeah, I realized all of a sudden that all I've been doing for about 6 years, has been just leading me towards a path that I would have never thought about. Because ultimately, what I was doing was concentrating on developing things to be more efficient, developing devices that would make those human robots to be more like us, more really like human beings. But yeah, that's great. Well done, you. Wonderful. But surely all of that knowledge, all of that expertise can be put into profit for other people, can he? So after having received that electric shock and rebuilding after that, I I very boldly asked him, oh yeah, okay, yes, you make a good point here, buddy. Well done. Okay, I got your point. But what are you doing? You said you're training, so you're going to compete then? He said, yeah, I'm going to Rio, and I hope I'll win. I said, well, yeah. Do you know what? Okay, let's make a deal. If you win the gold medal, okay, we discuss about doing work together. Yes, I should have done that, because he actually came back, and that man is actually Andy Lewis. He is the gold medalist of the last Paralympic Games that happened in Rio in 2016. And after he came back and after having the medal, he was literally shaking it in front of me, and he said, aha, what do we do now that I've got this? I said, well, we're going to sit down together and we're going to write a proposal, because well, I do want to do stuff with you, but we need to get some funding for this. We need resources. So yes, we sat together, and we had, as you can see, we had some good time at some points. Eventually, all throughout the research, and we managed to get some funding for 2 years. That funding was for developing the very first bio-inspired prosthetic joint based on someone's feature. When I say feature, what I mean by that was someone's dimension, someone's height, someone's bony structure, someone's ligament dimension, someone's tendons. That research that I've been doing over about 5 to 6 years, developing bio-inspired knee joint for human robots, was actually put into profit for Andy under the title Novel Bio-Inspired Smart Joint for Prosthetics and Robotics Lower Limbs, because yeah, let's just face it, I can't really stop doing robotics in a way. So we had that funding for about 2 years, And oh yeah, this is what the story is going to be a bit sad. I think it's going to go down a little bit. So we developed for Andy the very first bio-inspired prosthetic joint for him to be using and trialing for the Paralympic Games of Tokyo 2020. Yeah, I know. Sad, isn't it? Yeah, something just happened that just stopped all of us from doing that. Oh dear. Yes, I know. Yeah. Anyway, is still training and is still using it. So we are still going. Things are still moving forward in a way. But yeah, it's going to take some time before it can actually go back into competition and things, and when things go back to some sort of normality, as we know. But ultimately, yes, it will use it. So I'm now let me take you through what has been the consequence of that actual encounter with Andy, because ultimately that encounter led me to work towards rehabilitation. And what I found when I start looking into rehabilitation. Let me just give you some numbers, some figures here. Currently, in the UK, there is about 5,000 to 6,000 major limb amputation every year. Now, there is about as well, that means one amputation every 6 minutes. So someone is losing his limb every 6 minutes, if you think about it. 5,000 to 6,000 major limb amputation, coming from all sorts of causes, obviously, but ultimately these are the figures that we are facing. Low volume amputation has as we know, has a profound effect on activities of daily living, and not all amputees, by the way, are able to tolerate or even use a prosthesis. So that means that when surgeons perform all those operations, and when legs are being chopped, and people end up in situation where they can't do much about the way they are now, they have to recover. And there's an awful lot of psychological and physical rehabilitation they need to go through. When you look just at the technical side of rehabilitation, you realize that actually, over the last 200 years, nothing has really evolved. Well, you might see it as it evolved because we started with some crutches towards something that looks more like a springy leg that are being used by above knee amputees. But ultimately, those limbs are exactly the same. They perform exactly the same motion, and they do exactly the same thing. What hasn't really changed is the way we actually design those things. We don't really take into consideration the fact that our knees are really more than just pin joints. And what I call pin joint, I mean actually hinge joints. The one that you all know of, because I believe you all have doors in your house. So the hinge joint is what you use for opening and closing the door. So the hinge is that mechanism that allows the door to open and to close. So ultimately, what you're doing is you're having a joint that has a single rotational point. Now, the knee is much more than a pin joint. The knee is the embodiment of the bony structure, plus the ligaments, plus the tendons, plus the muscles. And the bones themselves have a particular shape. They are concave and convex. They roll and they slide. They also lock themselves. Yes, they lock themselves. When you're standing, I'm not going to ask you all to stand right now to verify that, but if you were to stand right now, when you're standing, you realize that actually you're not using any muscle power at all. Your knee locks itself. Yes, it does, because there is inside the knee what we call the screw hole mechanism that allows the knee to simply lock when you're passing a particular point of rotation. So all of that knowledge, all of that complexity, people would say, well, engineer would hate that word, obviously, because yeah, we don't like complexity in engineering. We want things simple so that we can control them much more. Yes, it's a reality. But hey, if we want to move the research forward, if we want to make things smarter, we need to embrace that complexity. We need to be able to analyze it, extract from it what is relevant, and then come up with some algorithms, some processes, some patterns that will allow us to understand a bit more. Not the whole thing, not the whole, having a holistic approach to this, but embracing some aspect of those beneficial features that we know are there in our bodies, in nature. Now, we are good in engineering. Let's just, as I said, we're good. Yes, we can do things very clever. We can do things very spectacular. Developing joints such as this one, which is a DARPA robot that can, even hold a grape, and the actual patient was using it was also able to tie his shoes as well. So, yes, great. I mean, it's wonderful. Well done. Yes, but as well, we know for a fact that all of those devices consume, and they really they require a lot of power, and they are not very efficient. They don't last very long, which is the reason why, by the way, we do not have them everywhere. If these were the solution, you would see, or everybody do not have an arm, to have them all around us, and we wouldn't even realize that these are actually very expensive devices because everybody got them. Similar with the lower limbs, or for either for above or below knees amputees. Yes, researchers are really active here. They do things incredible, and they also want to do, and they want to push that research forward. They want to even enhance the way we design joints, we design our companion. Yes, but I do not really trust that one on the right hand side here. I mean, I wouldn't let that happen to me. Even though I have, I'm working on that sort of with that sort of machine, I would not trust that for a minute. But hey ho, that's the future. Okay, this is where we're going. This is what we want as engineers. We want to be able to have all those incredible devices, incredible machines around us, so that they can make our lives better, and they will also enable us, by the way, to live more independently. Think about assistive devices, assisted living devices, smart houses, having the ability to talk to your house and having a companion that is capable to connect you with your family. These are the kind of solutions that we're going anyway. With the pandemic that we just had and we're still going through, these devices are being pushed, trying to be pushed more and more outside of the lab. But we're not there yet. We are not there yet. We know that. Now, we as engineers, we want to do more. We want to have devices that are clever, but we want, I think, above all, be in a position to eradicate, to remove what are the main problems for amputees or for people that are actually disabled. And the reason for that is because we believe that the answers to disabilities, or the answers to people that can't do things the way they were doing before, or the solution is really, or lies in technology. That's what we believe, again, as engineers. We think that we will end disability. I should actually say that, yeah, we will end disability by developing devices that allow people to have or to regain what they thought they lost forever, to incorporate or interface with our bodies, devices that we will connect eventually to our brain, so we can then control those devices, and the device will know what our intentions are and will enable us to do so. So we are getting there. We are close. I would say we are even close, very, very close, but there's still a need. There's still a great need for a better understanding. So those two examples here are the very, I'm going to say, the very latest one in terms of rehabilitation and enablement devices. But they have something is lacking for these two. With these two, is the fact that you can't use those devices for too long. They obviously require a lot of power, and they also heat up quite quickly as well. So these are among the few things that can go wrong with that kind of device, those kind of devices. Now, knowing what are our limits, knowing where we want to go, I think we need to go back to the basics. And when I mean basics, I mean we are all the fruits, we are all creatures on this planet. And this planet has been there a long, long time before us. And it's my belief that this planet has a lot more to offer. We need to protect the planet. By the way, I'm just giving my sort of green message right now. Yes, we need to protect the Earth. We need to be careful with climate change and all of that. Yes, but there's more with this planet that we can learn from. There is much more under each rock of nature. there is a lot of solutions for us engineers that we do not even think about. And I've got a bit of sad news for some of our mechanical engineers, which might be on that call right now. I'm about to disclose some information that you're not going to like. Yeah. Well, some others are going to be pretty impressed, I think. But there is something that you need to know about what we engineers think that we have invented. Now, as I said, we need to learn from this planet. We need to learn from the Earth because we have in nature an awful lot of solutions. Nature's inventions have always inspired. They've always inspired us anyway. Think about Leonardo da Vinci, and all these incredible, creations. He came up with this flying machine. He came up with actually the very first robot, I think, was actually drawn and designed by him. And that was, centuries ago. So all those inventions, all those solutions in nature have led to effective methods, structures, processes, mechanisms, and systems. And we know that there are numerous examples that we use in engineering. Think the Velcro. The Velcro is something that we use. I think we've all used the Velcro in our lives. There are numerous examples where biomimetic, which is the science of understanding nature and using nature for developing systems or developing engineering systems, there are numerous examples of biomimetic successes. Great achievements. The Velcro, which was developed by George de Mestral. So I think it was, 2020. So, about 70 years ago. Yes, 70 years ago. That Velcro was actually based on the burrs, hook-like, meshed, which can snag many type of surfaces. Yeah, he found that apparently on his dog. He found those little, plant on his dog's fur, and he thought, oh, very interesting. These little hooks can actually hook anything that is actually coming near them. So, and he came up with the idea of the Velcro. Then you've got obviously some of the recent development, which are the big dog robots developed by the Institute Boston Dynamics, which is now, I think, known as Google. I think they're being bought by Google now. But they've been developing incredible, devices based on nature, based on animals, not just dog, but also humans. I mean, they've got these huge bipedal robots that can actually even, do some. He can actually swing, and they also dance. They've got all those robots that can actually dance these days. Just Google it, and you'll find many different videos on them. But ultimately, the whole point of doing, biomimetics is because we have benefits with them: multifunctional systems, interdependent system, optimized system, compliant system. All of those features are actually in nature. Yes, they are there. Now, without any further delay, my dear fellow mechanical engineers, I will reveal this bit of a shocking news for you about one of the key, I'm going to say, achievement that we think, well, we assume that we came up with, we designed, we invented. If I was to ask the question to a mechanical engineer, what is the very primitive, the very first, device that we invented? The answer could be, or should be, I think, sprocket chains. But I think the very first one would be the gears. Gears, yes. Gears is something that, we've got everywhere when it comes to machines. We've got gears, in cars, in airplanes, in everything that is transmitting power or energy. You will find gears because they're very useful and they can, convey a lot of energy, a lot of power. Very useful. And we designed them. We invented them. Yes, we did. Well, we did, yes. But I have to say that actually these guys were there before. So this is Professor Burrow from the University of Cambridge, which will actually reveal the news. And I hope you can all hear him.
Well, we've discovered gears in an insect. Mechanically interacting gears are always thought of as a man-made invention used in our bikes and our cars. But what we've shown is that a small plant-sucking bug evolved gears long, long ago and uses these gears to mechanically synchronize the very rapid jumping movements of its legs. This is the first demonstration of interacting gears being used by any animal. The jump is really very rapid indeed. It takes off at a velocity of about 5 meters per second. That's equivalent to about 12 miles per hour. And it accelerates in less than a millisecond. So it experiences enormous g-forces as it takes off, about 500 or even 700 g.
Yes, I can hear the cry from your heart, my dear mechanical engineers fellows, and I do empathize. But hey, there is good news here, because it means that yes, we haven't looked under each rock of nature for solutions. Because yes, these were actually let me give you the name of the insect. It's called the Isis coleoptratus. Isis coleoptratus, which is actually what we call a plant hopper. They're called. Let me just give you the easy name here, the plant hopper. Yes, those are small hopping insects. They use tooth gears for their joint to precisely synchronize the kick of their hind legs as they jump forward. So that's what we did, you know, a long, long time ago, centuries ago. And this is what nature did many millions of years. So these gears were not designed. They are evolved gears, which means that we have to look further. And this is usually my message to my students. I usually tell them, do not limit yourself to what I'm telling you. Go out and explore. Go further. Search, seek. Sky is the limit when you have the tools. Challenge yourself. Go beyond the scope of what I'm telling you, because there's more. You've got more to offer. You've got much more to offer to this world that we have had, for all those many years. You're the new generation that is going to be taking everything to the next level, and we need you to dream big. You need to dream first. You need to dream the dream, and then eventually bring your engineering mind into play and come up with feasible solutions. Yes, but go further. Don't limit yourself to just engineering. Look at nature. Look at other fields of engineering. Now, this research in biomimetics has led me to identify some key features that has then led me to develop that bio-inspired prosthetic knee joint that I am going to show you in the next slides now. So this is kind of the whole research that has been going on, and how you go from knowing what nature is doing to identifying the key features and simulating system, simulating device, and simulating your actual solution, then testing it, building it, and so on. So there's a process that obviously comes into play when it comes to engineering that you need to follow. So this is really the process and the way you would undertake such a solution. You always start with, what is the problem? So defining your problem, defining what you need to look into, and then you would come up with some solutions. Those solutions are always the fruit of a particular process. Analysis, then a comparison, then identifying what are the requirements, coming from the requirements, the engineering specifications, moving towards solution concept, then simulation, design, and then building and then testing. Now, those different areas have led this research to go even further. So looking into how can we include in our way of designing, way of doing, patients, because ultimately, as I said at the beginning, we want to do things for people. We want to be able to come up with solutions that would be useful. That's the reason why we want to keep the patient in the loop. And that's how we call these kind of approach. It's the patient in the loop approach. Now, when you want to include the patient in that sort of loop, you need then to do some extra work with them and also on them, I would say, as odd as it sounds. Yeah, we need to work on the patient himself or herself. So we then have to extract some particular features, particular ways of moving, simulating their different parts of their bodies, and then going further in terms of analyzing the way their bodies are. So going and investigating and doing some MRI scan analysis on the way their bones are working, the way their ligaments are, then attaching to them some what we call sensors that will detect their movements. So doing some motion analysis, which is what we did here with Andy Lewis in the Bristol Robotics lab during this project for developing the bio-inspired prosthetic joint. So at the bottom left, you've got Andy changing legs, which has been one of the also focus of this project, enabling him to change legs rapidly. So the ultimate goal of the project was obviously developing a bio-inspired knee joint that enable him to do both cycling and running, because he's a para triathlete, which means he goes from swimming to cycling to running. In the meantime, as he was training, for the Paralympic Games, he wanted us as well to look at the way he's changing legs. So we also looked into how can we make that changing of legs very, very quick. So when it comes to working with people, you realize that actually there's so many things that we can do. They really want to engage as well. They're really keen of people or researchers that are actually listening to them, because sometimes they just think that they are not being heard at all. So then all the fruit of that research, we came up with the very first bio-inspired prosthetic knee joints, which is all purely based on these dimensions, on these features. So you can see the femur, which is the top part here of the prosthetic joint, and you've got a tibia. And inside, maybe, I'm not sure if you can see, but maybe you can see them from the side view. You've got what we call the cruciate ligaments. So for those of you who are not familiar with the cruciate ligaments, basically in sport, if you say you torn your cruciate ligaments, that means your career is finished, because those ligaments are key for guiding the motion of your bones. So if you lose one or if you torn one, you're out. So me doing this research for about 5 to 6 years on it, I realized that yes, you need to understand those in order for you to develop an actual suitable mechanism that will allow the joint to move as our knees, because our knees are rolling and sliding, which is what this joint is actually doing. It rolls and it slides as well. And it also locks in straight position as it is now. Now, with this research done with Andy, I also attracted the attention of another patient who will turn out to be also part of the Team GB later on, part of the shooting Team GB, Miss Tanya Goddard, who used to be working in the police task force. And what she said to me the first time I met her was, what you're doing is great, with Andy. Well done, you too. You're developing for him a great joint. He's going to win again. Well done. But the problem is not about the prosthetic joint. Stop working on that, please, and listen to me when I said that the problem is actually the socket. The socket is the real problem. So she said, please, please, please have a look at what we've got here. So I sort of felt for her, and I just said to her, I said, well, I can have a look, but I'm not going to make any promises on what I can do. And she said, please, could you just analyze and tell me what's going on inside, because I'm suffering after only 2 hours wearing it. What I found is when it comes to socket, like the above knee socket, temperature rise by, I think it goes all the way up to 46 to almost 50 degrees after a patient wear those sockets for about an hour and a half. Imagine yourself wearing your shoes, and all of a sudden, after an hour and a half, the temperature goes all the way up to 50 degrees. Yes, exactly. You're going to take them off. You're not going to keep them on. Absolutely not. No. So that temperature rising, including the sweat that comes up when they put on their liners, you end up with an awful lot of pain, an awful lot of problems inside the sockets. So the experiment that we did was doing things the other way around. Instead of analyzing and looking at the design of the socket itself, we asked her to walk around with the actual socket, and we put some sensors in, and then we measured the temperature. We measured everything. And then we said to her, okay, now the problem you've got here is that there is a socket, there is a liner, and there's what you do with the socket. There's a lot of things going on, So ultimately, we found that actually things need to change with the design of those sockets. We need to make them much more bio-inspired. There needs to be some ways to include the fact that temperature and pressure creates all those problems with the socket. So using what we call some machine learning algorithm, we identified and we use the algorithm to alter the initial design of this socket. So the software told us that if you consider the pressure and the temperature, this is what your socket should look like. Now, include that socket within our test rig facility that we've got in the Bristol Robotics laboratory to test joints, which is the test rig that you can see here on the right-hand side. The whole idea here is to bring together the way humans are walking, are running, and making that platform, that test rig, to be able to mimic the way they are actually using those devices. Now, include some machine learning algorithm that will be able to be trained and to be able to undertake some movement and make the facility, make the rig to move like we move. You end up with a rig or a facility that will ultimately anticipate all the problems that we need to be facing, we need to be overcoming. So looking at the future, what is it that we do once we can develop such devices? Well, I need to make a disclaimer here. This is a video showing how or what the future is regarding prosthetics, which includes some dissection on the residual limb, and it will also include some integration of screws into the bones. So I hope you don't mind. If you don't want to look at it, don't look. But that's a short video showing what we call osteo integration. So we will be looking at what is the remaining of the bones, and then we will be integrating an actual stem that will be inside the bone, and then will give us the interface to be able to attach then bio-inspired prosthetic joints, making the device to be completely merged into the body of the person. And then ultimately, the whole point of doing that is because we want to develop a system that would be human-based, that will be useful for people. It's all about the people. It's all about the way we can develop smart and safe systems, the way those systems will ultimately be used by us, used by people that need those systems. So doing things smarter, doing things, integrating everybody's abilities as well, integrating the way we understand nature is, in my opinion, the future. Based on those, you can then, again, sky is the limits. You can develop concepts to integrate features coming from nature. You can also develop compatible mechanism coming from engineering, and you can then incorporate that separation of mechanism and the structure itself within your device. Also, you can involve the performances of your device, and all of that these are the different aspects of the research that would be ultimately undertaken by the next generation of engineers. Integration and extension of that bio-inspired approach for other devices, such prosthetics or exoskeleton. So again and again, the whole point of this research is about the impact. It's all about what is it that we can do for our people, the people that need what we are doing, the people that are ultimately using those devices that we are developing. And yes, we will then change the world. We will change the world, and our next generation of engineers will change the world. Our students will change the world, and they will make things differently. They will make things much more efficiently, make things that are even beyond the scope of what we thought about. If and only if we empower them. We need to empower them. We need to give them this zeal for always striving for better system, or better, I'm going to say, smarter system. Thank you all very much for having listened to this presentation, and I hope you enjoy that, and I hope you've got some food for thoughts to share with your students. Thank you all.
Oh, thank you very much, Appolinaire. And if everyone wants to unmute and clap, that is absolutely